Welcome to Math 104, where we're talking about cubic and quartic regressions. So this one is going to be a quick video because we're getting the hang of these regressions. Really, I think you're hopefully you're just noticing that it's just one button that is going to make the difference between the quadratic model. So once we get the hang of that, then we're moving on to some other models as well. So this particular one says the percent of US population that were foreign-born in the selected years from 1900 and projected to 2020 are shown at the table below, where X is the number of years after 1900s. We have seen that sentence before. What does it mean? That just means that these values, instead of having 1900, we're going to start at the year 0, 10, 20, and so forth. Now be super careful. Don't automatically assume they go up by tens just because the first row does. Just be very cautious. And then the one below it, we are just talking about your percentages. Don't change these values. They're it as they are. Now, when you go to build a window, the last ones we've seen, we said, okay, well, these numbers are on the one on the very start is the lowest one, and the one on the very top is the highest number. That's going to be different for depending on the number or the models that we're going to be choosing. So definitely look within to see where your smallest and largest numbers lie in order to get a good window. So perhaps in here, I've already entered in our data. I've double checked it. Make sure that yours are also double checked as well. We want to make sure that your scatter plot is on before starting. And then when you hit graph, if you still don't see anything, that's because your window is off. Now your X window, your X values, they start at 0 and they go all the way up to 120. That's a pretty big gap. So maybe we actually go in the negatives. We start at -20. The reason for that is I'm going to go up to about 150. And when I change my scale, actually, I like 5 as my scale. It's going to allow me to jump several places at once. Towards the end of our model, you'll see things that are kind of switched together because we go from 2010 to then 16, 17, 18, 19, 20. So those values might look a little squished, but that'll still work well for the data that we're going to be seeing. Now your Y minimum, our smallest Y value is 4.8. So let's just start at 0. And if you wanted to get a little bit closer to the 4s, that is totally okay. Let's also look at your highest value, which looks to be about 14.7. So something a little bit higher than 14. It's pretty close to 15, so I wouldn't even start at 15. You might want to go up to 17 or so. And I apologize, I've already done this window. That's why my scales look the way that they do. But when you're noticing your Y values, notice that we go from 13.6 to 14.7. And it's not exactly, I mean, in this case, it's a little bit more than 1. But when you scale, it determines how nicely your values are going to be. So the increments, let's take a look at another one, 12.2, and then it goes to 12.4. That's not an increment of 1. So perhaps your increment for your Y scale, you go up a little bit smaller. So about 0.1 might be the trick. So sometimes you won't have to go big, big, big. You can be actually a very small number for your scale. Let's take a look at your graph. And notice that by that scale, we're able to have a nice curve. We see the whole big picture. We may have gone too far to the right and maybe to the left, but I'm not so concerned about that. The big idea here is to make sure you have an appropriate window to see which models you can go ahead and choose. Now, taking a look at this graph, what models do we think would work? So do we think, could this be a line? Absolutely not. A line will not work. What about a quadratic model? Well, a quadratic, right? Quadratic models. And if I were to draw really quickly what I might be seeing on my screen, and I I wish I had a calculator right in front of me, but they kind of look like this. They're gonna get like squished together, right? So they kind of look like this. So a line, no matter how you draw it, won't be able to capture this. So line will not be a good model. Let's see, quadratic, either up or down. A quadratic, while it does have that nice curve aspect that we're seeing, it only has one turning point. And here we can see we have multiple turning points. We have 1, 2, 3 turning points that we know of, and our quadratic model only has one turning point. So when we come up with a list of reasons why quadratic might not work, it only has one turning point. Or data is not straight, but curved. What other models do we think might not work, right? So we did linear, we've done quadratic. Do we think a cubic could work? Depending on the cubic per graph, cubic could work. So let's say cubic, it does have some turning points. It is kind of curvy. Not all cubic ones look exactly like this. This is just a general shape. After cubic, we have quartic. Do we think quartic could work? Quartic could work. That's the one that kind of looks like a W, kind of like that. We have multiple curves. These look great. You could, if you wanted to, we haven't really done any, but if you wanted to expand your knowledge, you could do quintic, which is essentially very similar to this one. It's just to the power of 5. If you wanted to expand it there, up to you. We've really just kind of stopped at x to the 4th models. So quartic. Do we think exponentials or logarithms, right? Exponentials, even if it were to go down, right, there's too many curves, or if we went up, definitely doesn't work. Logarithmic, logistic, looks something like that. So these ones would not be a very good fit. Exponential goes up or down rapidly. Data does not have a dramatic increase or decrease. Logarithmic, they don't have, this one doesn't have a flatten out. Data does not flatten. Versus logistic. Students always forget about logistic. This is the one that looks like an S. Data is not exponential with flatten at the end. So some kind of explanation, however brief, okay, just say, give a small explanation as to why some of these won't work. So that means it's really up to 2, cubic and quartic. So we might have to do a few bits of interpretation to see what is the better of the 2 models. So in order to do that, right, we've picked perhaps 2. Now let's compare the 2 together. So let's go ahead and hit second mode. Let's go back to your values, and let's go ahead and pick a regression. Which one do we think right now is the better fit? I'm going to just start with cubic for right now. So let's go ahead and hit cubic. Okay, list 1 is my x values, list 2, perfect. Let's go ahead and store your equation. All right, right there you see your equation. Definitely jot it down to the best of your ability. I'm also going to take a look at right here, right now, your R squared. We don't have R, so we can go ahead and find that by rounding to 4 decimal places, 7, 6. Oh, that would be 7, 7, 0, 0, I guess. So 0.769 next to the 7 is, or sorry, next to 7 is another 7. Oh, wait, that's why. 6, 9, 8. There we go. All right, so have we seen one that has 0.8773? The ones we have had before have definitely been well into the 9s. 8, 7, 7, 4. So cubic has a correlation coefficient of 0.8774. Is that what we said? Correct. So right now, what are we feeling about this correlation coefficient? Do we think it's a good fit? Only one way to guess, or one way to tell. Based on this, I'm going to say, no, it's not a very good fit. It's going to go through a few bits of our data points, but it's going to miss a good number. So again, it's going to go through a few, but it's going to miss a big portion. So we can automatically rule this one out if we wanted to, and then go on to quartic, which could be a better fit. But this is kind of showing you what we can do if we're between values. Now your project will have you compare throughout. So if we wanted to, we could continue to find your average error, which I'm going to show you here, going through it with a quartic. So let's go ahead and go back. Instead of cubic, we're going to go to quartic. Again, just making sure that list 1 and 2 are there. Let's store your equation one more time. If you wanted to, you can make a comparison and put it into Y2 if you want.
We literally start and go all the way through the end of our tax workflow, right?
Okay. All right. So if you're ever wondering as to what the structure might be of these ones, not only do you have your notebook to go back and double check, but these ones here up above, oops, right in pink at the very top right here, it's going to tell you the structure. So A, x to the 4th plus B, x to the 3rd, and it's going to tell you what is listed. Now, if your calculator runs out of room, it might say ... So just kind of scroll down. This is kind of what we're looking for. So let's go ahead and grab your correlation coefficient while we're at it, 9875. Definitely is stronger, but not the best, right? 0.9942. So a little stronger. Let's go ahead and get that visual. Okay, so 100% stronger than the one before. It hits a lot more values, but you'll notice that it's still hitting a few over to the left and to the right. Oops, I just messed that up. So still not a perfect fit. I'd say it's a good fit, not an excellent fit by any means. So now that we have that visual idea of what it looks like, we have your correlation coefficient. Let's go ahead and put in your average error. So we're going to go all the way up to list 3, where we hit vars, yvars, function, y1, parentheses, oops. Second one, close those parentheses. Just double check that they're kind of close. Your correlation coefficient did suggest that they would be pretty close, and a lot of these are. Going up to list 4, we're going to subtract list 3 by list 2. And again, you'll notice that these values are small. It's okay if it's negative. That doesn't matter one bit. Let's go out and hit second mode, then stat, calc, one variable statistic. Change this to list 4. And then what we're searching for is this number here, 0.3139. We can just round to 2, so let's just say 0.31. So the average error, 0.31. If we wanted to compare it to the cubic, we would see that this average error above here would be a lot bigger than the one with your quartic. So now that you've had a visual aid, your correlation coefficient, your average error, you can then determine that a quartic is the better of the two fits. Again, you would have to roll through this whole thing though for your project.